All right, thank you all for coming. I'm Cameron Murray. I'm an assistant professor at the University of Arkansas. And today I'm going to talk about some work that goes back over the past 4 or 5 years related to using BCSA cement for structural concrete. And I want to acknowledge a whole slew of graduate students listed on the slide here that have helped out with this work over those years. I kind of have a lot to get through, so I might be going kind of fast, but hopefully that'll leave some time for questions at the end. So I thought I would start with the ACI code. This is the code that governs how we design concrete structures. And in the 2019 version of this code, there were a bunch of changes. One thing that's relevant to this session was they added some language about using alternative cements in structures. And so it says here, alternative cements shall be permitted if approved by the licensed design professional and the building official. And it kind of has some wishy-washy language about exactly how you would decide if the alternative cement is suitable to be used for structures. Fortunately, there's a really good article published in Concrete International at about the same time that's kind of a supplement to the code. And it talked a lot about a lot of these factors. Specific to structures, it talks about axial strengths, compressive strengths, flexural strengths, shear and torsion, ultimate stress-strain relationships, volume change, modulus of elasticity. It also goes into a bunch of other stuff like fire and durability that are pertinent to structures. But I'll be talking about this kind of stuff today. And in our lab at Arkansas, we've addressed several of these things, and I'll talk about some of that stuff here today. So I guess this begs the question, why would we want to use this cement in a structure? And I guess I would never argue that this is a cement that should completely replace Portland cement, but there are certain applications where it may be, a suitable replacement. And that's things like precast, pre-stress, and structural repairs, in my opinion, because those utilize its special properties like low shrinkage, fast setting, and fast strength gain. But obviously there's a lot of practical questions around whether the properties are similar to Portland cement. So my introduction to this was when I was a graduate student at the University of Oklahoma, and I was fortunate to help out with a couple projects looking at pre-stressed concrete using BCSA cement. So on the left, we partnered with a local precaster and made kind of structural scale precast concrete elements that were pre-stressed with BCSA cement. It was kind of a feasibility study. On the right, we did more of a lab study, really looking at bond between strand and concrete and flexural strengths a little bit. And we found that the cement had improved pre-stress losses compared to Portland cement because of its low shrinkage primarily, good flexural strengths, and good bond with strands. So this kind of encouraged me to continue down this path of looking at this cement for structural applications. So from our work at Arkansas, I thought I would start out with some practical mixed design type of concerns. Obviously, mixed design is important for casting structural elements. We need mixes that have the properties that we need to satisfy our structural requirements. So one big thing is setting time. At room temperature, the cement will set up in like 10 to 20 minutes with no retarder, so we generally always retard it. We've also found that temperature is an accelerator of setting time, so at higher temperatures, the cement will set up more quickly. So we've done a bunch of setting time tests. This shows at 100 degree Fahrenheit ambient temperature, different water temperatures, 100 degrees, 75 degrees, 40 degrees Fahrenheit, and a bunch of different water cement ratios, what setting time you can expect. So if it's 100 degrees outside and it's 75 degree water temperature, we would use about a 0.5% citric acid by cement weight to get about 60 minutes of setting time. Most of the time in our lab, normal lab temperatures, we use something like 0.35% citric acid, which gives us around 45 minutes of working time. So we try to work really quickly. Another kind of practical concern is slump. We need an adequate slump if we're going to place concrete for a structural element. It's got to form around the rebar and all of that. So for Portland cement, for a 1-inch nominal maximum size aggregate, we have a curve like this. This tells us if I use 325 pounds of water, I should get a 3-inch slump. This is like first step of mixed design. So we did this kind of testing for BCSA cement. We find that for 0% citric acid, so no retarder, slumps are very low compared to Portland cement. Partly this is because with no citric acid, the slump retention, really kind of sucks. It starts to set up really quickly. It's kind of interesting, if we add citric acid, it makes the mix a lot more fluid, so we get a big increase in slumps. And if we continue adding citric acid, the slump increases even more. So This is kind of useful just for determining initial mix design parameters, getting the slumps that we require, and the setting time that we need. Another thing we've looked at is just compressive strengths. That's obviously really important for structural design. So we've done a bunch of testing with different citric acid dosages, different water cement ratios. If we use our 0.35% citric acid and it's room temperature, and we use a 0.4 water cement ratio, we can exceed 4,000 psi in 3 hours. So that's generally what we're aiming for, because this kind of maximizes the benefits of this cement, the really, really high early strength. And at 28 days, the strengths are very good. You see we had 2% citric acid here. The 3-hour strength is like 0, but the strengths are good at 28 days. So that's just kind of background. I want to get into really the structural applications now. So when I arrived at Arkansas, the first study we did was with a grad student named Gabe Cook. He made a bunch of reinforced concrete beams. They all looked like this. They were about 12 feet long. They were 6 inches wide, 12 inches deep. We made some tension-controlled and compression-controlled specimens. And I'll just show the tension-controlled specimens here. And we made them with Portland cement and BCSA, and we tried to keep the mixtures very similar so that the properties would not be affected by mix design parameters. So the first thing we looked at when we tested these beams was just qualitatively, what does the cracking pattern look like? Are we seeing things that look like flexural failures? So this is one of our Portland cement tension-controlled beams. This is a BCSA beam that we tested like as soon as we could get it out of the forms and put into the load frame. So about 4 to 5 hours after casting. And you can see very similar behavior, distributed flexural cracking. The cracks are about the same height, similar number of cracks. That's all good in terms of the flexural performance. And this was true when we tested our BCSA beams at 1 day of age as well. So, the performance is just as good after they start gaining strength. We also look at load versus deflection. This is a good way of seeing if the performance of the beams is similar to Portland cement. So here's the Portland cement beams. Here's the BCSA beams that we tested at about 4 or 5 hours of age. And you see they plot right on top of the Portland cement beams. And then these are the BCSA beams that were tested at a day of age. So the performance of all these was very similar. A couple places we really look at are where the cracking occurs down there at the bottom, where yielding occurs. It happens at similar loads and deflections, and then this ductility out here that's indicative of a good tension-controlled reinforced concrete failure. So it's very similar for Portland cement versus BCSA cement. So we also look at just moment capacity. We divided the experimental moment capacity by the nominal moment capacity, so greater than 1 is good. And they were all greater than 1. And you can see this ratio is pretty similar for the BCSA beams as it was for Portland cement. So the code equations are just as conservative for BCSA as we would expect them to be for Portland. So another kind of cool thing we found, we looked at this thing called the ductility index, which is if we take the deflection at ultimate load over here and divide it by the deflection at yield, we get kind of a scalar value that tells us how ductile the beam was. And we found that the BCSA beams were more ductile than the Portland cement beam, or beams. And this improved over time, so they became more ductile after 1 day. And it's kind of interesting because these ones were actually weaker concrete than the Portland cement beams. So in spite of it being weaker concrete, we had more ductility. And the only way we could really think to explain this is maybe it had something to do with the ultimate compression strain in the BCSA cement being different from the Portland cement concrete. So this led us to want to investigate this further. And the Alternative Cement Committee supported an application to a CRC research project, so we're happy to be working on that now. And in this project, we're looking at the flexural stress strain characteristics of BCSA cement. So we're kind of emulating some research, a test setup here that was done at NC State University in the early 2000s. And they were emulating work that goes all the way back to the 1930s when they were developing the strength design methodology in the ACI code. So the idea of this is we put a big axial load on the specimen and then we apply a load over here to put a moment in the concrete. And this concrete portion is meant to represent like the top part of our concrete stress strain diagram for a beam. So the part of the concrete that varies from 0 strain up to 0.003, the ultimate compression strain. We know the stress distribution looks something like this, and we estimate it with this thing. So we're kind of seeing if BCSA works the same way as Portland cement, if these parameters also work for BCSA cement. So there's what our setup looks like. You can see it looks really similar. So I got some cool videos. This is my favorite part. So this is full speed. Okay, play. So these are fun. This is why I like doing this stuff. Well, I say they're fun. They're kind of scary. I'll watch it again. So those are like about 220,000 pounds of axial force. Get a slow motion video here. There's some strain gauges at the top and bottom. And we have a digital image correlation system that measures the strains on the top surface there. Yeah, these are cool. I could watch these all day. So that's kind of on the flexural strength side. And that project's ongoing. I don't have any results to show from that yet. We hope to finish our testing on that in the next month or so, and our report's due in October, I believe. So shear is another thing we're interested in. So after we did the flexural strength study, I had another student work on some shear strength. So we made these beams. They have the same cross section as our flexural beams, 6 inches by 12 inches. But we put the load closer to the end. We used a shorter span, and you see there's no shear steel here. So we're just looking at the component of the shear that comes from the concrete alone. So first we look just qualitatively, crack patterns. This is one of the Portland cement beams. And here's one of the BCSA beams. So you can see all our failures were kind of characterized by a big shear crack that went, more or less from the load point down to the support. They were all very similar. We compared these capacities to all the code equations. So Portland cement's over here, we tested at 28 days and 1 year. BCSA we tested at 1 year, 28 days, 1 day, and 3 hours. And these are all the average of 2 different beams, so there's a little bit more variability in a couple of these BCSA ones. So we compared these to the modified compression field theory in AASHTO. This is kind of like the best existing equation to calculate the shear strength of concrete, and you can see, it calculated the strength of the Portland cement with similar conservatism as the BCSA cement, more or less. This is the simplified method in AASHTO, ACI 318.19, ACI 318.14 detailed, ACI 318.14 simplified, and the Eurocode. So if you're not used to looking at shear, all the shear equations are like super conservative. So you can see that we're underestimating the capacity by quite a lot. That's sort of by design. And you can see that for all of our BCSA specimens, the conservatism is pretty similar to Portland cement. So the equations appear to work the same way for our BCSA cement as they do for Portland. So in conclusion, so far from the testing we've done in terms of flexural and shear strength, the code equations appear to be adequate for BCSA cement. We're getting similar results as we'd expect for Portland cement. We have that ongoing work looking at stress strain for BCSA cement concrete. And also Betty talked about her work looking at repairs with BCSA cement. And I talked about some of the unique mixed design considerations. I actually think that's a strength of BCSA cement compared to some other alternative cement technologies. It's sort of like Portland cement. You can buy it in a bag, you mix it with water, it makes concrete. So it's a little bit simpler than some other alternative cements. So I want to thank all the people that funded the research, and hopefully I have time for one question maybe.